Just in case some of you forgot who is who on the stage. Professor Stefan, guten Tag. Professor Atsushi Miyawaki, konnichiwa, right? Konnichiwa, yeah. So Professor, Dr. Eric Betzig, okay? Yeah, hello. Okay, so any questions from our audience and the friends from the Korea side? Yeah, so feel free to raise the questions.
Hello.
Yeah, hello, yeah.
Hello, my name is Hyunjun. First of all, thank you for your valuable lecture. I asked to Dr. Eric Betzig. You said that you did experiment in your living room. As I know, DIY biology is a trend nowadays. So what is the advantage and limitation of it? Do we need academia and lab to succeed in biotechnology? Thank you.
I'm not sure I quite got all the question, but it's about if I understand the advantages of working in one's living room versus working in an academic setting. Yeah, okay, well, the disadvantages of working in your living room is you pay for it all yourself. The advantages that was honestly the funnest time I've had in my life. Harold's been my best friend since the late 80s, and when we were in his apartment doing that was clearly, I mean, you couldn't do that. You couldn't have that much fun in academia. And the thing is that if, like I said, if we had to write a grant or do whatever or do this in a normal system, it would just take too long. I mean, we could just be so nimble in what we're doing. And another problem that I see in science is in some ways we're almost too connected. I mean, we heard Barry Sharpless say this morning about getting out on the boat and disconnecting. I think that's a very important thing to be able to because otherwise you get too much input and you start to think too much like everybody else, is that you need a certain degree of isolation to come up with a different idea. And working in one's living room is about as isolated as it gets. So.
Does it answer questions?
Okay, thank you. Bye.
Thank you. Any questions from our side? Yes, please.
Hello, my name is Kim Min-seok from Yangjeong High School. I want to ask to Dr. Eric, you was failure, isn't it?
What was it?
But you didn't give up to doing your job. I want to ask, what was the reason that you didn't give up?
That I didn't give up? Well, in some ways I'd say I've given up twice already, okay? I mean, I gave up near field because, but again, it's like I said, there's this country western song, you gotta know when to hold 'em, when to fold 'em. And so one of the things that they teach you in science, and the whole purpose of a PhD is really nothing more than learning perseverance. You know, is to keep working at a problem for long. And so they drill that in your head, but it's also important to know when you bump up against the laws of physics or some perversity in your biology that means you're not going to do it and you have to switch. But you can't let that, you know, again, I think that my failures were the seeds of every success that I had afterwards. So another good example with the near field is one of the other reasons I left near field was because when I got like that cytoskeletal picture that I showed, that was like the best example out of 50 cells I looked at, because the problem wasn't the microscope, it was the labeling technology was so poor that you wouldn't see it at the diffraction limit, but with near field you'd see it was, so, you know, that was another source of failure again, but it made me, it's so that when I heard about GFP, it was just obvious that it had to transform microscopy because of that specificity is perfect. And so I just say to you again, you know, choose hard problems And don't be afraid to fail, because it's the failures you learn from, and that's what will lead to an eventual success.
Okay, thank you very much.
Thanks. Yeah. Yes?
I'm Yangjeong High School, and my name is Jung Won-gun, and I have question to Atsushi Miyawaki and Dr. Very hard to read. Dr. Atsushi Miyawaki showed us some particular cases such as zebrafish, etc. for fluorescence imaging technique. Would you also give us some example of field in human body?
Okay, I didn't get the last part of it. So zebrafish, yes, imaging I showed you,
Yeah.
and then
For fluorescence imaging technique, would you also give us some example of field in human body?
oh, human. Okay, so at present, so the like a systemic application of the GFP, so to human being, is kind of negative. Many people are negative on that. So whole body in becoming green or yellow. That's very unrealistic. Okay, but by contrast, so the topical application, local application, focal application of GFP, so to some specific or so cancer cells or some tissue. So that's going to be very, I think, in not before long. So it's going to be so applicable. So that's my current opinion. So there will be another types of the technologies that allow us to switch on and off, more freely. So gene technologies will be more applicable. So that's my opinion.
So you could turn yourself green just for a date on Friday.
Yes. Or cell type specific or so temporal specific regulation will be more and more powerful from now. And then, so to some extent, so that kind of technologies are promising.
Thank you very much.
Actually, from today's talk, I find something very interesting, right? Why the two speakers are more on the optical principle and the physical principles. One on more on these proteins, right? So let me raise a question. For example, while Professor Hell has been devised a very new technology to look deep into and with a high resolution of the cell and the tissues. So how many proteins in your experiment, right? How many fluorescence dyes has been successfully response to your mechanism?
I think it's very important to understand that STAT per se, or stimulated emission, is a very fundamental mechanism that can apply to any fluorescent protein. But the on and off switching that we've seen, I mean, the one that Atsushi demonstrated first with the drone is of course very, very important because as I mentioned, it allows you to turn the molecules on and off at very, very low light levels. And currently, I would say I know of 6 or 7 switchable fluorescent proteins that we can turn off at very low light levels, and a number of them are growing. But from the organic fluorophores, basically everyone can be turned off by stimulated emission. So it's very universally applicable. I think this is very important.
Thanks. Yeah. I hope everybody remember the step, right? The stimulated emission diffraction, right? Yeah, it's a very new kind of technology. Thanks. Yeah. Any comments from the other speakers?
Well, I would just say how microscopy is connected to labels again. I mean, everything that Stefan and I do is based on label technology, and it's the limitations of these techniques today are really about the labels still. And so, we're completely dependent on guys like Atsushi and others who develop new labels either this way or through, organic chemistry and so forth. So I think it's one of the most important problems, and obviously I'm prejudiced, but one of the most important problems in chemistry is labels for biology. It's really key.
Yeah, just adding to that, you can change imaging completely by becoming a chemist. Yeah. So this is very, very important because the molecule determines in the end the resolution. In the past it was the lens, now it's the molecule.
Yep.
Yeah. Okay, looks like the goals behind, right? You have questions? What? No.
I have a question. Yeah. I have questions. Okay.
Maybe we can host, a few more questions, please.
Hello, my name is Yu Shi, a freshman major in material science. I also inspire a lot from the career path of Dr. Eric. And my question about the extent of independence. We know that science nowadays has become more and more complex, and teamwork is a kind of necessity, and staying with others will provide a sense of safety. But following the crowd will also make us lose our creativity and critical thinking. So to which extent, or how can we balance these two things?
That's a great question, and there's not an easy answer. You really have to go with your gut. But for me personally, I find that there's times in my life when I have to be connected enough to the rest of academia and the rest of the scientific community to kind of pull ideas from. But then I need to disconnect to see the synthesis and the combinatorial combinations of those ideas. And you know, you can really only do that when you're alone and can think it through. So it's a balance. It's hard to say, but the problem in modern science, I think, is not to be connected to other people. We're connected all the time. The problem is to find and carve out the time to be disconnected, to be able to think things through. So. And again, I'd just like to stress this combinatoric aspect of science. I mean, for me, that was really illuminating when I had been away from science for so long. I kind of felt like Rip Van Winkle, waking up and seeing all these new toys and technologies when I started looking to get back into science that didn't exist 10 years before. You know, not just the fluorescent proteins, but, you know, new types of lasers that made fluorescence much easier, and so forth. And again, science is so amazing because when these guys came up with the photoactivated proteins, nobody was thinking of this as a tool to change resolution of microscopes. You just never know where an idea is going to lead, and that's one of the greatest things about science.
Yeah, thank you.
Thanks. Yes.
Sorry, hi. My name is Wensin and I'm from RJC. I have two questions.
Could you please, move close to the microphone? Yeah.
Oh, okay. I have two questions more specifically to Professor Miyawaki. The first question being, in the diagram which we saw just now, the cells, when they proliferate, they were green in color, but when they stop, they were red. Is there any explanation behind this? Like, what are the factors affecting these changes in color?
Oh, you are talking about the color changes in cells. Which one?
The cancer cells.
Cancer cells. Okay. So the cells expressed food. So which I mentioned. So the food stands for fluorescent ubiquitination-based cell cycle indicator. So it can sense or it can report the progression, cell cycle progression. And many cancer cells divide very rapidly. So therefore, those cells emit green fluorescence more than red. Okay. So please remember that. So one of the slides which I showed you. So the red color from G1 phase and the green color from SD to M. So the fast dividing means more cells stay more than time in SD to M. So therefore we can easily identify the cell cycle speed just by color, so that the cells emit. So that's the mechanism underlying the imaging techniques.
Sorry, one more question in the same note. Like, Because this is actually effective in showing the presence of cancer cells in the body, do you think this could one day possibly lead to like the injection of these protein in vivo to show to reflect the presence of cancer cells in the body? And how efficient do you think this will be when comparing to current imaging techniques for detection of cancer cells?
So you mean you're asking me about the efficiency of the gene transfer? Is that right? Because when we inject the proteins, so you like to compare the efficiency with the transfer rate. What is
as in, like, because as you mentioned just now, the protein can actually show whether the cell is, is it a benign tumor or a malignant tumor. So this is applicable in the detection of cancer. So do you think this could be done in vivo rather than in vitro? And how efficient do you think, if this can be done in vivo, how efficient do you think it is in detecting cancer as compared to other techniques?
Well, it totally depends. So the detection efficiency is, if we discuss that, we need to take many factors, into consideration. And let me see. Wow. So recently, quite a few people get interested in cancer stem cells. So cancer stem cells now sleeping, but it can provide the very rapid growing cancer cells in some time. Okay. So therefore, I think it's relatively easy to distinguish between the slow dividing cells and the rapidly growing cells, but very hard to detect. So potentially, in the future, potentially, becoming the cancer cells. So that's going to be very hard. But maybe you can catch me after this session to discuss the first part of your question. In terms of the detection efficiency between the fluorescence image-based technologies and other technologies, there are many items to discuss. So let's talk later on. Catch me.
Yeah, let me also share with your questions. Actually, I believe your question be further packaged into the localization of the proteins. When you talk about the protein reaction to the fluorescence dyes, it's not totally different between the animal model and the human being, and the in vivo and the in vitro testing. It is from our experience in the National Cancer Center for our research, we find that the major difference is the pattern of this fluorescence within the cells, or in other words, just now I mentioned the localization of the proteins. That gives a lot of information. Yeah, I hope it further clarify your questions.
Okay, thank you.
Thank you. Any questions? Because after the break, we have another big dialogue sessions. So I think if you have further questions, we can continue the discussion, more meaningful talking after the break. So for time being, let's thanks again for our three great speakers. Yeah, see you later. Yeah.